Toronto and who spent almost a year in 2015 at least, so it's a familiar place to many of you. Over to you.
Thanks, Laurent. Thanks for attending the talk, coming here. I understand it's just after Easter, and sometimes it's Easter vacation. So what I want to talk about today is about community structure in social information networks. It's really kind of part of a bigger kind of a research question or a research adventure that we're doing, is trying to understand social networks. Okay, and it's not something you can do in, I don't know, in one step, but it's a bigger effort. So it's a long-term research project, and we're still at the very beginning. But it's something I'm really excited about. It's something I'm passionate about. It's not an easy problem. For some reason, I feel I really would like to try to understand social networks. And it's something that I started during my sabbatical in 2015 here. Maybe some of you remember me bubbling about social networks and things like that. Everything was still kind of very confused. There is now a little bit more progress. There's still more to be done, but it's also kind of an opportunity to tell you guys a little bit what happened, and that maybe it makes sense, maybe something can be done. So that's a bit the background. So the goal is to kind of, it's really about social networks. So that kind of, it's my personal view that there are a lot of interesting research problems in understanding social networks. And when I talk about social networks, I talk about online social networks like Twitter, but also everyday social networks that we have among human beings. Okay, it's interesting these days, whenever I say social networks, everybody assumes it's online social networks, and everybody forgets about everyday. So there are interesting problems. Maybe something, I don't know, which is a bit controversial, is I would like to make the claim that we can understand both online social networks and everyday social networks, are a useful tool to understand these networks. It's actually mathematical modeling and analysis. So we can take kind of a rigorous formal approach to it. Okay? And depending on your background, you say, sure, we can do that, or you say, wait a minute, that seems bogus. Okay? And also kind of something I would like to highlight, that if we can do that, so basically that's what I try to do, use mathematical modeling and analysis to understand social networks. If we can do that, it would have a big impact. Both kind of just the understanding of social networks, kind of what they are, why we have them, how we form them, but also in order to create algorithms that we can use in practice. So this is kind of the vision, the goal of the research. In terms of outline of the talk, I first want to give you an introduction to make a bit more precise what are the problems we want to look at, why we want to look at these problems, and then give in the second step, present the first simple model to kind of mathematical model for social networks. Okay. And I go in two steps. So first is a description of the model and the results, more from a higher level. And then if I get there in the second step, there will be more a detailed model this detailed description of the model of the results, where there's going to be some math. Okay, to show you there is indeed some math behind it. And then also talk a bit about future research. There's still a lot to be done, but kind of my point of view is this first model, even though it's very simple, it's promising. It's kind of a first proof of concept that maybe something can be done. Okay, so that's really kind of the nature of the talk. Hopefully to convince you a little bit, I'll give you an idea, maybe something can be done. It's not completely hopeless. Okay, does that make sense? All right, so let's see. Okay, so introduction. So if we look at social networks, let's say everyday social networks, they are important. Okay, so I don't want to go into there too much because I don't understand too much about it, but I think from a biological point of view, I think what separates humans from other species is our ability to have complex social networks. Okay, that I believe that's something we can do that maybe other species cannot do. So kind of, it's to human beings, social networks is a defining feature. It's something very, very important to what we do. There has been a lot of research and results on social networks, I don't know, for a long time, both in social sciences, more recently also in computer science. Okay, especially in computer science, because now there was data available from Facebook and Twitter that people can analyze. So there has been quite a bit of interest, but despite that, there's still open questions. Okay, and I have the feeling there are in particular two kind of areas where there's still a lot of research to be done, and there are still a lot of interesting questions. So one would be to create predictive models for social networks. So I don't say all of them, but there are quite a few examples when there are mathematical models of social network, they're more descriptive. So for example, there was an experiment of the small world phenomena that when you send a letter from somewhere in the world to somewhere else, it gets there within 6 steps. Okay? And then there was a model by Kleinberg to explain why this is possible. Okay? But this model was specifically to explain why this phenomenon is possible. Okay? There were some other experiments where people saw that when, let's say, the diameter of the network, so this 6 degrees, as the network becomes, you add more and more nodes, the network gets denser and denser, the diameter shrinks, I believe. And then there were graph models to show that under these graph models, you get that type of property. So there were a lot of mathematical models like that that were targeted to explain a very specific property of social networks that we are already aware of. I don't know too many mathematical models that were used to predict or to identify new properties of social networks that we did not know before. Okay? And that's the goal we would like to do here. Is this possible to create the model that allows us to predict new properties of social networks that we are not yet aware of? Okay? And this is basically what physics does. Okay? So physics, I mean, black holes, it's not something you wake up and say, sure, there should be a black hole. There was a lot of kind of mathematical model to say, okay, there should be a black hole. And then people discovered or showed it's indeed true. Okay? Does that make sense, what the goal is here? Okay, so that's the goal. Maybe you say, wow, this is very ambitious. You know, that's crazy. How could you ever do that? But that's the goal, okay, to create these predictive models. Okay? The other thing is to also create more precise or formal definitions of concepts of social networks. Okay? And here the inspiration comes a little bit of information theory. So I mean, one thing about information theory, I think one contribution of Shannon and the people who created it is that you take a word like information that people use all the time in everyday life, and they believe they know what it means, to give it a very precise mathematical meaning. Okay? And once you give a clear mathematical definition of what is, how do we measure information, suddenly you can do a lot of things. Okay? You can talk about compression and things like that. Okay? But you only can do that because you have a very precise mathematical definition of information. Okay? And now we want to do something similar for social networks. Okay? And maybe again, I don't know how you feel, but sometimes when I talk to people, say that's impossible. Okay, social networks are very complex, you know. So for example, examples that we're interested in to give a clear definition is influence. Okay, so there are algorithms to find influential people or to maximize influence or something like that. Then you ask, okay, give me a mathematical definition of influence. Okay, people say, look, you know what I mean. It's something like this, it's something like that, and we model it in this way. Okay, it's a bit heuristic, you know. Then maybe you say it's impossible to really define influence very precisely because somebody maybe is influential to you, but it's not influential to me. Or maybe yesterday they were influential, today they're not influential. So it's something very subjective. How can you put that into a precise mathematical definition? Okay. But I would say it's similar with information. You know, information, you could say it's something very subjective. Now, I give you some information. Maybe it's good information for you, and it's bad information for me. Maybe it's new information to you, and it's all to me. Okay. But it's possible. So I believe creating these formal definitions for social networks like influence and things like that is not more difficult than creating it for information. Okay, and to come up with a mathematical definition of information, I think it's not trivial at all, but it could be done if that's possible. Maybe you also can do something here. Okay, so these are kind of the high-level questions that we like to do, and the question is, can this be done? Okay, is this just Peter having crazy ideas, or is that really something that can be done? Okay, does that make sense? So that's the goal. Okay. Now, if we could do that, I feel there would be impact. Okay, it would help us to, similar to what in information theory, once you have a definition of information, you can talk about coding and this in a very formal way and show, do things much more efficient. The idea is once we have this type of models and definitions, it could help us to come up with more efficient algorithms for community detection, identifying influential users, identification of popular content early on or things like that. Whatever we want to do, let's say on online social networks, suddenly we can do it in a very formal way, or we can do it in a formal way. Okay, so there would be impact there, but there also will be impact on the understanding of social networks, let's say everyday social networks. Okay, so I don't know how you feel about it, but sometimes I ask people, why do we have social networks? Okay, and I get very different answers. There doesn't seem to be, a clear understanding why do we have social networks, what is the purpose, and things like that. And it seems a bit strange to me that something that is so important to us, we have a very weak formal understanding, much weaker than of physics or chemistry or things like this. But it seems that social networks are just as important to our everyday life, like physics and chemistry. Okay, does that make sense? All right, so that's it. So the idea is, look, these may be the questions we ask. These seem to be difficult problems. But if we can make some progress, there will be some important impact, so why not try it? Okay, and that's kind of the attitude. Let's try it and see what we get. Okay, does that make sense? Okay. So let's see. So the idea is now, okay, so how would you even get started? Okay, when you talk about models, mathematical models of social networks, what you're talking about? Okay, and so we said, okay, let's start, but in order to get started, let's be a little bit more modest. Okay, so one thing is interesting, I find interesting. When we say social networks, it's not a well-defined term. Okay, if I ask you, define me what is a social network, I would get very different answers. Somebody said, okay, it's a graph. Okay, well, maybe say, no, a graph is not enough. There also needs to be it's not well defined what is a social network. And maybe one reason is that a social network, let's say everyday social networks, maybe serves different purposes. Okay, so we said instead of looking at general social networks, let's look at information networks. Okay, so information networks would be social networks that we need in order to share or exchange information. Okay, so it's a more clear goal. It's really the sharing of information. That's the goal of why we have that network. So it's a bit more precise, and hopefully by kind of making the scope a bit more narrow, it's easier to make progress. Okay, so that's kind of one simplifying assumption that we mean maybe there are different purposes of social networks. We're looking at the purpose of social networks to share information. Okay, in the online world, Twitter would be the prime example of a social network like this. So Twitter, it's about tweets, sharing tweets. It's about sharing information. Does that make sense? Okay. And the hypothesis is that when we form social networks or information networks, we don't do it in a random manner. We don't do it nilly-willy, but we actually try to do it in such a way that we do it optimally. Okay. So the idea is why we have social networks. They're so successful and they help us so much. Is they're an optimal solution to a problem. Okay. Does that make sense? Do you buy it? Okay. So maybe that's another question. So anyway, so look, I also have difficulties sometimes to convince myself that this is really working. Okay, it's not that obvious. If you don't have the solution, you don't know whether it's going to work or not. Okay, so something I find interesting, if I would tell you, and I think people look into that, let's say in a beehive, how a bee communicates. Okay, they need to find honey, and they communicate where the honey sources is. I think if I would claim the way they communicate with each other in order to find the honey, they do it in an optimal way, I think you would buy. Would you buy it? You say, okay, of course. Over evolutions, P learned to do that in an optimal way. If they wouldn't be here anymore. Okay, there would be another type of bees that are organized much better. They would find all the honey, and the other bees that have a suboptimal solution don't exist anymore. Okay, so I find it interesting. Sometimes when we talk about the animal world, and we say they do things in an optimal way because they have to survive. If they don't do it optimal, they would not survive. People do buy it. Okay. On the other hand, if you go to human beings and say what we do is optimal, the way we organize our society and all that is optimal, then suddenly it seems more harder to believe. But anyway, that's the hypothesis here. Okay, so what we do is, maybe it's it's either optimal or close to optimal or informed by an optimal solution. Or in other ways, anyway, that's the hypothesis. We're not suboptimal. Okay, we emulate something that's close to optimal. So that's a hypothesis. So that's a hypothesis. Okay, and it's a hypothesis on which the solution approach is based. It's actually impossible. It's important. If we would not have that, it would be difficult to make progress. The approach that I'm going to discuss. Okay, and then you have to say, okay, what's the problem that we're going to solve? Okay, and in an information network, the problem to solve would be efficient distribution of information. Okay, so that's what we try to solve, and it's a distributed information. It's basically all users or agents or people in the network. They create information, they consume information, they're interested in certain type of information, and they create links with other agents and exchange information with other agents in such a way that it's optimal for them. Okay, so that's the idea here. That's the optimal of the problem we're looking at, efficient distribution of information. And the idea is each agent makes decision in order to maximize their own utility. And once you have that, and you see that, then you can analyze the problem using game theory. Okay, so you have agents that have a utility. Everybody acts to maximize the utility. So what's the outcome in terms of the network topology that we get? Okay, and if you believe this and you believe that, then you can. Then you see, okay, now we can create a mathematical model to analyze the problem. Okay, does that make sense? Do you buy it? Okay, we can discuss it. Okay, but that's the approach. And the big question is, you see now this is basically a computer science type of problem. You wanna analyze it, and the question is, when we analyze it, game theory, Nash Equilibrium, does the Nash Equilibrium that we get from this mathematical analysis, does it have anything to do with what we observe in real life? Okay, so that would be kind of the test, whether this really can be done, whether the solutions that we get are informative of what happens in real life. Okay, and that would be a good model. So a good model is a model that if you analyze the models, you get answers. These answers are useful for the application that you're looking at. And so that would be the test. Okay, questions? Yeah, it's good time to...
To understand, so you speak about an optimization problem. So I see the objective function, every agent maximizes its own utility, but I guess there is some constraints. Is there a limited number of links or something like this?
We're going to talk about that. Okay. Yeah, of course. I mean, this is just the big flavor. I haven't specified the detailed model, but that's the idea of the flavor. We're going to, I mean, you see, we're going to define a utility function, and there we have to be careful. I mean, there could be different type of utility functions, and that's another test we have to do. We have to come up with something that is useful, so when we get the answers make sense. Yeah.
Is there always a Nash equilibrium, or in some cases can there be there's always one?
We will see. Okay. So look, this is on a high level. I just tell you what we would like to do. I haven't defined yet what the utilities are. Okay. And you could see, depending on how I define the utilities, maybe you get a Nash equilibrium, you don't. Maybe the outcome you get has something to do with reality or it doesn't. Okay. So as part of the modeling is to choose these. To define that whole thing, in particular utility function, in such a way that it leads to an interesting problem definition. Does that make sense? Mm-hmm. So this is not the model itself, it's just the overall approach. So the overall approach is important, is we believe what we do is optimal, we do it in a distributed way, so we can formulate it as a game, and then we can analyze Nash equilibrium. And then ask the question, what we get, is that useful or not? So to some degree, it's nice. It's a very simple test. Okay, give me a model. Tell me what the Nash equilibrium is. I'm checking it out, whether what you predict has anything to do with reality. If it does, looks promising. If it doesn't, it doesn't. Okay. Does that make sense? Other questions? So that's good. Yeah?
Yes, sorry. At this point, we don't know yet if at each step of the process, every agent takes simultaneously a decision, or is it iterative? It's not yet.
No. So I'm still motivation. So it's on a very high level. Okay. So I mean, look, I don't know. I mean, so I'm not sure how you feel, but sometimes when I talk to people, they kind of say, "Whoa, what are you doing? Mathematical modeling of social networks? That seems crazy." So I just want to kind of give you a flavor of what the approach is, rather than boom jumping into the math, to kind of motivate what we try to do and how can we test what we did, whether that makes sense or not. Other questions? Okay, so let's see. Okay, so now the first model. Okay, so kind of a bit more detail. So we're going to talk about information networks. So there are agents. I call them agents. You could do individual users and so on. They create information and they consume information. So it would be like Twitter. You write tweets and you read tweets. Okay, so that's the intuition. Then also an important part of the model is that different agents have different interests. Okay, in Twitter, not everybody has the same interest. Somebody's interested in sports, somebody's interested in politics, and so on. So we have a variety of interests. Okay, and also agents have different abilities to create content. Okay, maybe I'm an expert in sports, so it's easy for me to write tweets about sports because I know a lot about it. Maybe not much about politics. So I could write tweets about politics, but they would not be that interesting. Okay, so that's important. So there's a set of agents or users or individuals with different interests in consuming content and producing content. Okay, I kind of feel this is not super controversial. That's something I believe you would agree with. Okay, and then the idea is also that when you are part of the information network, there is a cost for consuming content. Okay, so it could be just a time you have to dedicate to read tweets. Okay, or I think we as researchers know. I mean, in a research environment, you could say producing content is writing a paper, and consuming content is reading a paper. Okay, and reading a paper carefully, it's a considerable cost. Okay, reviewing a paper is a considerable cost. Okay, it's not free. But you get a reward. If you read a paper and say, wow, this was interesting, I learned something new, or this is really useful, you get a reward. On the other hand, if you say, wow, what's that? You won't get a reward. So that's the idea here. So whenever you read a piece of content, you pay a cost. And depending whether you say that's interesting to me or not, you get a reward or you don't get a reward. Okay, and then basically you can see a little bit here. Okay, you get a utility for content consumption is reward minus cost. And also for the production would be kind of how many people find your content interesting. Okay, so you could say I'm happier or I get a higher utility in a research community if my papers get accepted to conferences. I go to a conference and everybody comes and says, hey, I read your paper, it's a great paper. Then you get a lot of utility. On the other hand, if you in a research community, you submit to conferences, your paper never gets accepted. Once your paper gets accepted, you give the presentation and nobody's in the room, then the utility you get would not be very high. Okay, and you would ask yourself, oh man, should I keep on doing that or not? So that's roughly the idea. Okay, does that make sense? So these are kind of the intuition, kind of the where we start with assumptions or axioms of an information network. And then what we have to do is you have to translate that into a mathematical model. Okay, the next slide tries to do that. So what we have to do is we talk about interest. So we have to be more formal. What is an interest? Okay, and an interest, we assume here there's a topic space. Okay, there's a space of interest, and each point in that space would represent a particular topic. Okay. Also, what we want to do is we want to measure distance between interests. We say some interests or topics are closer related than other topics. So wireless networks and wireline networks are maybe closer related than wireless networks and red wine or something like this. So there's a structure in these topics. They're kind of something. Okay, and the idea is we capture that. We assume that topics live in a metric space. Okay, and we have a natural way to compute the distance. So that's kind of how we measure, or that's how we model topics. Basically, topics are pointing in a metric space. So that's the first mathematical model. Then the next thing is that now you give me an agent, I have to characterize the agent. And what I do is I associate with each agent kind of their main interest. So it would be one point in that metric space. It would be the topic they're mostly interested in. Okay, does that make sense? Does that make sense? Okay, and then also what we have to do is we have to define what's the utility function for production of content and consumption of content. And also we have to decide what's the strategy space of the agents, so kind of what decisions can they make. And here the people who produce content, they can decide which content should I produce, and the ones that consume is which agent should I connect with, so I get the content I'm interested in. Okay, does that make sense? Yeah.
Does it might be maybe a very question that you might be explaining later on, but does this model consider heterogeneous social networks? Let's say, like you were saying, like the cost for consuming information might be that is agent independent. Now, if I take a information let's say online network, and I take a actual social network, like I'm spending time reading a paper affecting my social life, so that's social network basically. So does it answer this heterogeneous kind of interaction between two networks?
No, there's no, okay, if I understand your answer correctly, you say there's an online social network and there's a real life social network.
Paper, I'm spending some time to
no,
that affects my other social networks and then...
No. You see that no, okay, it doesn't mean there should be, but you have to see that's, so the type was a first very simple model. So the idea here is to create the simplest model possible. And the simplest model possible, we feel there is only one network. And the defining features of the model is really there's a cost for there's a cost for consuming, there's a reward for producing, and different people have different interests and different things. So we feel these are the properties that have to be there. If they would not be there, it would not make sense. Okay, let's say if consuming content would be free, it would not quite make sense. If there would not be a reward, it would not make sense. If everybody would have the same interest, it would be too trivial, it would not make sense. So maybe I should have highlighted that. So this is kind of the simplest model where we feel these are the properties we have to have, kind of the fundamental properties. If one of these properties is missing, it does not make sense. But of course, we could add much more other things, but we don't do that. So it's the kind of the first model. Does that make sense? Excellent. So let's see. And so this is the model. But now you see you can play with. So you can come up with different metric spaces. Okay, you could say, let's look at different metric spaces to model it. You could have different utility functions. So even though that's kind of the outline of the model, the mathematical things that have to be there, you could still fill it in very, very differently. Okay, and depending how you fill it in, you maybe get different answers, or you will get different answers. Okay, but these are the ingredients of the model, and hopefully, when the intention here is when you see that, you say, okay. This, I can see how we can translate that into a mathematical model, okay? That kind of, does that make sense? Okay, all right, so let's see. So the next thing I want to do is, so we analyze this for a particular model, okay? I want to come back to the particular model, but the next thing is I want to discuss on the results that we get kind of on a higher level, okay? So I think, because I feel kind of the results are important. How you get it. So one thing that is interesting, so once you have that model, you can define, you have a game, okay? And you can ask what's the Nash equilibrium. So one thing is that when you analyze it, community structures emerge as a solution to the Nash equilibrium, okay? That maybe seems trivial, okay, I don't know, but I think it's nice, which shows that look, we have communities in social networks. It seems to be universal. You could ask the question, why do we have communities? And this answers it that communities are a Nash equilibrium structure. Okay, so we should expect that we have communities because it's a Nash equilibrium. Okay, maybe you say it's trivial, but I'm not sure whether I ever saw a formal derivation that shows that Nash communities are indeed something that is stable or optimal in some way. Okay. Also, what is interesting, I think, if you look at the Nash equilibria, they maximize social welfare. Okay, even though everybody acts selfishly, it's good for everybody. Okay, and it seems that's another kind of an important property for social networks to be useful, is that I feel it's what's optimal. If I act in a selfish way, we all do very well. Okay, if that would not be the case, probably this type of social networks would not be very desirable. Does that make sense? Okay, so I don't know. Does it make sense or doesn't make sense? It's right, okay. No, so this is the outcome. So that's the first result. So communities are indeed the solution concept of this. So you could say the model at least does one thing correct. It predicts correctly that there should be communities. Okay, so at least it passed one test. Okay, if it would not show that there are communities, you could say it's not a good model. Okay. The next, so this is probably obvious, you know, but if you look at communities, basically in a community under a Nash equilibrium, the producers and consumers have similar interests. So indeed, that's what the community is, people with similar interests. Okay, that's what you expect. Now this thing, the next thing is interesting, and that's what we felt was a problem with the model. Okay, so the outcome of the analysis is that each agent specializes on, everybody that produces content on a very specific topic. You know, we really specialize, you zoom in on one topic. And I told my students that cannot be true, you know, that there's something wrong with it, okay? You know, where is the problem, okay? But then it was interesting, so we looked at some papers, okay? And there's actually one paper by Laurent and Eidg that make this assumption, is that in a social network, you produce content on a very narrow space compared with the space where you consume content. Okay? And there was another paper where people made the same assumption, is that the content that you produce in a social network is much smaller than the set of content that you consumed. And they used this as a hypothesis or as an assumption to do the analysis. In order to back it off, they actually did experiments on Twitter. And they looked at Twitter. I mean, you can look at the Twitter feed. You can see what is the content you consume and what is it produced. And they say, okay, what you produce is much more narrow compared with what you consume. And they use this as a validation that this is a good assumption. Okay. So what we then say is interesting here. This is actually a formal justification of this assumption. Indeed, it's optimal to focus on one topic. Okay. Now, I believe as researchers, this makes sense. Okay. So if we are researchers, we go to a conference, I don't know, control theory, okay? There are many different aspects of control theory, but typically you say, look, what I want to do in order to make a name for myself, I try to focus on certain things, okay? So for example, matching in bipartite graphs. Okay, I want to become an expert. Now it makes sense. You want to become known for one thing that you do very well and being recognized for this, okay? So it indeed seems to be something that we do.
So the content is the interest here, isn't it?
Say it again.
The content is the interest.
Oh,
the interest is different from content.
What do you mean? Okay, so that's an interesting question. When you say the content is the interest, what do you mean?
I mean, like the agent is producing a content, it means that he is associated to certain interests.
In the very beginning?
In the very beginning, but when he is producing, I mean, that is interest in the sense of consuming. Interest in what sense? Both producing and consuming. You are associated with both cases.
Okay. Okay. So there are topics.
Okay.
So there are topics. I'm interested in certain topics when I'm consuming. And I decide to produce content on certain topics when I'm producing.
Oh.
And so what we say here is basically, when I'm producing, I'm going to produce I focus on one topic.
Okay.
Even though I could do several things, I focus on one topic. Okay. And this is not something you would so this was to us was surprising, and it seemed to be true. Now, also what is interesting here, so coming back to what you said, is we associate each agent with a main interest. Okay. So let's say I'm a researcher. I say I'm really interested in I'm really interested in TCP. Okay. That's my passion. Okay. That's really what I want to do. But I realize the reality is if I produce papers on TCP today, it will be hard to publish. Okay? So as I look, in order to be able to publish something, even though I would like to do TCP, I'm not going to do TCP. I'm going to work on social networks. Okay? And this is actually what happens here, is the optimal thing for the agents to do is not to produce what they have the highest ability to produce, what they really want to produce, but to adapt according to the demand in the community. Okay? So you adapt what you do towards the interest of the community. Okay? So basically as a researcher, we say, let me look at the papers that I got accepted in the conference I go to. Now, which topic, I want to do something that is interesting, but also something that's likely going to be published, and there's a trade-off there. Okay, and you try to create you want to make an optimal decision there. Okay, does that make sense? Okay, so that's something that comes out of the analysis. Okay, because everybody produces content, adapts to the community. What's going to happen is that the interest of a community gets concentrated around the main interest. Okay, so I don't know, at NIPS there could be many different topics, but right now deep learning is popular, so it's really concentrated around deep learning. Okay, and everything else tails off. So that's kind of there's a concentration. It gets pulled in. So there's an attractor that and it pulls in the content to a quite a narrow topic compared with what people in the community are really interested in. Does this make sense? Is it? I don't know. Is this understandable, or is it too obvious, or is it?
Yes, it's clear.
It's clear. Okay. So maybe I'm over. And because also, so I'm going to be a bit more precise. Because it's getting pulled in, there's going to be a separation between communities in terms of the content that is being produced. Okay. And a clear separation. So basically, what he says, there's no overlap, or a very small overlap in the content that is being produced in the different communities. Each community focuses on unique content. Okay.
Thanks a lot. What you claim is that to exhibit some communities, you will try to find flows of information between the consumer and producers concentrated around the same topic of interest, basically.
I'm not sure. It's not that I want to look for it. The Nash Equilibrium tells me that is a Nash Equilibrium. This is the characterization of a Nash equilibrium, that people produce in such a way and content is concentrated in a community in this way. Is that what you meant?
Yes, more or less, yes.
Yeah. So basically that's all I'm saying right now. If I can do an analysis, what's the Nash equilibrium? And these are the properties of a Nash equilibrium in words. So these things are happening. Yeah?
Your model is an agent. Can an agent participate to different communities, or?
I leave it open. So it's going to be an outcome of your optimization problem. Okay.
So did you make some models that make possible quite often the fact that agents are participate to the different communities? Or?
So I'm jumping ahead now. So we're going to use. So these results come from a very simple model, and under this model, you're in one community. And this is a limitation of the model, okay, that we are aware of. But there is kind of one limitation here. Other questions? Okay. And another thing is, okay, I find this kind of, that's one outcome. So I'm not sure, but maybe you heard about that. So people observe, okay, in a social network, you connect. And some people say it's not clear, why do you, and they also say that people that connect are similar. Okay, and they have similar interests. Okay, they post on similar things, but even more so. I mean, but I'm not going there. They said if the way people you connect with, everybody either seems to do a lot of sports or no sports. Okay, they all seem to smoke or not to smoke, things like that. You also adapt behavior and things like that. So there's a correlation. And the question is, okay, do you connect because you do the same things? Okay, and that's why the connection is there. So you're interested in sports, you do a lot of sports, and that's why you connect. Or is it you connect, and when you connect, you're getting influenced to change your behavior so that everybody does the same? Does that make sense? And to say, basically say, look, you can't tell. If I just give you the outcome, you cannot tell, did you create the connection because you had similar interests, or do you have similar interests because you were interacting with each other? Okay, and they kind of say this chicken and egg. Okay, is it homophily or is it influence? Okay. Now I find this interesting. What this result tells you, it's both. Okay, you first connect because you have similar interests, and once you connect, your interest gets even closer aligned. Okay, so it's actually both effects, but that are at hand here. Okay, it's not one or the other, but they're both together.
Varying with time, it can be influenced. The actual influence could be to change in the utility function of the users.
No, right now we assume your interest is it's fixed. Now everything is fixed.
How can you talk about influence in that case?
Say it again.
How can you say that there is an influence if you do not change the value of
Because I say, look, I say I really want to write papers about TCP. Reality is nobody's interested in TCP. All my friends are interested in social networks. I'm going to write about social networks. Or I'm really interested in machine learning. I want to do, I don't know, what is an old topic? I want to do logic or something like that. But I realize I cannot publish at NIPS. So let's do a deep learning so we can publish. So that's the influence. It's the influence of the community. You adapt to the community. Okay. Does that make sense? So these are the results here. Okay. And there's something else is that, so we have utilities, and in a community, different people get different utilities. Okay. And what is interesting that these utilities provide a ranking function for agents in a community. So we can use this utility to describe the rank of a user. Okay. And it's a natural way to rank users and to differentiate users. Okay. Does that make sense? Okay, maybe I talk too much. Okay, so why are these things interesting? So I just want to highlight a few things. So one thing is that interesting that because the content is concentrated around, for each community is concentrated and distinct from another community, so we can exploit that for community detection. Okay, so we say, look, if we do community detection, rather than just looking at the graph structure, we're also looking at the content that is being produced and exchanged. That should help to find out what the community is. Okay, and so here the example would be, let's say you go to a university, UNST, and all you would see is the graph of how students interact with each other, and you want to do some analysis, you could do. But if in addition for each student, I don't just say who they connect with, but also I tell you which classes they are taking. I think then it would be very easy to say, okay, this student is in computer science, this student is here, and this student is there. Because the classes in the different departments are quite separated. Okay? So the idea here is if I don't only have access to the graph structure, but also to the content that is being produced, basically that's what predicts community protection should become much, much simpler because you really have this distinct set of content in the different communities that are characteristic for this community. Okay. Another thing here is kind of these utilities. We also can use that to do community detection and also to find influential users and so on. So the point here is that this what we have here it's actually useful. Okay, it describes what's going on, but it's also useful to come up with algorithms later on. Okay, does that make sense? Okay. One thing is there is always under the model we have, there's always a Nash equilibrium, but the Nash equilibrium is not unique. Okay, there are many different Nash equilibria. Okay. Now, what is interesting that under some Nash equilibria, some agents are not part of any community. Okay. And again, look, we did the mathematical analysis, and one student said, look, it can happen that there are some agents are not part of any community. And again, first the reaction was, you have to hide the result. Okay, that does not make sense. This is not what's happening in reality. Okay, but then we thought about it and we said, okay, maybe it's true. Okay, and for example, I don't know. Okay, so anyway, we're being taped. Okay, so in Canada, I think Toronto is in Canada. So in Canada, I believe, and there's a problem, or Canada has a problem with the native people. Okay, the native Indians, and right now they live in reservations. Okay, but they really, to some degree, they're marginalized from Canada. Okay, and I think it's a big problem for Canada how to do that. I think nobody is happy that they kind of are a little bit isolated, marginalized, but nobody knows what to do to change it. Okay, and I think in the past different policies have been tried, and some of them have failed very badly. Okay, had very bad outcomes. So, but here the point is, this is actually true. Okay, it could be, it indeed could. Or here the point is, now that we thought about it, I think. So what this tells you, having a community structure where some people are marginalized, not included, is indeed a Nash equilibrium. You can show more. It's a stable Nash equilibrium. Okay, and maybe it says, look, it should not be surprising. I say each society has a problem that some people are marginalized. Okay, I don't know. I'm making now big claims. Okay, but it's just there are people who are homeless. or things like that. The people are marginalized. And maybe you say, look, they're lazy, they're this and that. But maybe it's actually an outcome of the structure of social networks, that they have the tendency that some people who don't fit in the focus of the society, they're really getting marginalized. Okay? And this is what we're going to present. So there's the GameNets conference coming up, so we're going to present this result here. But this is, I find this kind of an interesting outcome in terms of understanding of real-life social networks. We should be aware that people being excluded maybe is the norm and not the exception. It's just part of what can happen.
It's not true for everyone who's not got a Twitter account.
No, anyway. So I'm taking you seriously. No, it's not about this. It goes further. It's really, so something, so as a student, okay, go into social science and studies, okay? And there's so often people, I mean, there's the notion of people who are marginalized. They're excluded from society. And often it's elder people, they're kind of disadvantaged people, immigrants, and they're basically isolated. They don't have a social network anymore. They kind of just live on their own. And it's not just a question of Twitter, it's also, and people identify that as a problem in society, are these people that are really excluded from, they don't participate in society anymore. They're literally little islands.
That's not true of the Indians in Canada. They live together and they've got their own.
Yeah, but they're separated from the rest of Canada. Yeah.
I'm not in Twitter, but I'm in another.
Yeah. So it could be both. It could be as a group, or it could be as individual people. Okay, so that's kind of, first I thought, okay, this is strange, but now I believe maybe you should take it seriously, that this is indeed something, it's the norm. In these social networks, these things tend to happen. Yeah? You're not part in any community.
The Indians are very much in their own community.
Okay, so maybe there are two levels. Okay, very good. There are two levels. One is you individually marginalized, or you as a group marginalized. And okay, it's a good observation. And maybe, it makes sense. You can be both as a group marginalized or individually marginalized, yeah. So the different levels, yeah.
So with respect to some social network or class of social networks, they're marginalized. Universally marginalized.
So under this model, but it's a simplified model, they would be universally marginalized. Okay. But of course, it's a simplified model. There's certain aspects that are not there. But that's something that's happening. Does that make sense? Okay, how much time do I have? Okay, all right. So these are the outcomes, okay? So I'm not sure, maybe I talked already a lot. But it's kind of, so this is the results. Here's kind of some speciality. Now, what we do want to do next, so I tried to say a little bit, okay, this makes sense. There is some relation to what happens in reality. The real test is the next thing, to kind of do, okay, there's some additional studies we want to do. For example, what's the dynamics of how information spreads within a community? I haven't talked about that. Dynamics of how communities forms, I haven't talked about that. And also the hierarchical structure of communities, okay? And in the hierarchical structure, it could be that there could be one community that excluded from the hierarchy. So that would be the natives in Canada. So that will come out, and we saw that phenomena in hierarchical structure, that there are some communities that are an island. They're not incorporated in the bigger community structure. And but this is kind of this is really the test whether it's useful or not. To, for example, and we try to do that right now, to use these outcomes, so this description of this Nash equilibrium, to come up with community detection algorithms, okay? And something that is interesting here is we want to use localized community detection algorithms, where you only need to know information about the node and the local neighborhood of that node. And then you want to use this information to kind of jump, and get closer to the core, to the community at each jump. Okay, and once you have the core, you can get the whole community. Okay, so this would be interesting. So you can do community detection. You don't need to know the whole graph, but you only need to know local neighborhoods. Okay. And I'm not sure whether this is the other one. So this is a project with a company. They have online forums. They want to understand online forums. So we use these results here. And that's another thing I wanted. Is Ludovic here? Hi, Ludovic. Okay, yeah. Excellent, yeah. So Ludovic is going to do a project in Toronto in the summer, and what he's going to look at is at this problem here. Okay, that some individuals are marginalized. Now the question is, can we implement some social policies to get them back into the community with as little as social cost as possible? Okay, and how can we do that? So instead of physical policy, how should we change taxes and things like that to stimulate the economy at the lowest cost, or how should we tax and things? Would be how can we change kind of things like this to bring these people back in? And the nice thing here is it can be formulated as an optimal control problem. Okay, and that's good. So can it be done or can it not be done? Okay, all right. So maybe just quickly. So this is the detailed model. So it's a very simple model. We wanted to start with the simplest model possible, so the analysis is as easy as possible. Okay, so what we said we want to use. So we want to have a metric space. Let's use a one-dimensional metric space. Also, let's not have any border effects. So basically, you look at the ring. Okay, and the topic is a point on that ring. Okay, and then the distance between topics is just the distance on that ring. So that's what we start with. And because of that, we don't have why we don't have hierarchy and things like how it comes for this. Basically, agents produce and consume content, and basically each agent is characterized. Content is characterized by a point, and each agent is characterized what's their main interest. Okay, but the idea is so each agent has a main interest, but also they're interested in other content. But the interest in other content is smaller the further the content is from their main interest. Okay, and also if I produce content, agent Y produces content X, the further the content X is away from the center of interest, the lower the quality of the content that I produce. Okay, so that's kind of how we model it. We also assume right now to make it similar, easy, it's kind of a continuous model and agents are uniformly distributed over that ring. Okay, so there's no kind of concentration. Then agents can form community. A community consists of a set of consumers and producers. If I'm a consumer, I can say, okay, for each in a community, how much time do I allocate to consume content in that community? How much time do I allocate? If I'm a producer in a community, I can say, okay, at what rate do I produce content of type X? Okay, how many papers do I write on this topic? How many papers do I write on this topic? And so on. I have to see. Once you have that, if I give you a community, you can say, okay, what's the demand function? I can look at all the agents that consume content, how much time do they spend in that community, and how much are they interested in content X. So that would be the demand function. So if the demand is high, agents that spend a lot of time in that community would have a high interest in that content. Okay, does that make sense? It's kind of it's a demand function. And similarly, we can define a supply function, basically in community C, at which rate is content of type X being produced. Okay, high quality content of type X. Okay, so it's kind of supply and demand. It's a bit like an economic model. And then you get a reward 1 if you get interesting content, consume interesting content, you get a reward 1. If it's not interesting, the reward is 0. And there's a cost C that's less than 1 for consuming content. Okay. And then now you can kind of utility function is for consuming depends on how much time do I spend in a community. And so this is the supply in the community for topic X. This is how much I'm interested in topic X, so that's my reward. That's the cost. Each content of topic X gives me a cost of C, so that would be reward minus cost. Okay. And if I produce content, is how much content do I produce of type X? What's the demand for that, and how good I am at it? Minus the cost. Okay, I don't go into too much detail here, but this would be the utility kind of reflecting this. And then what you would have, so agent can decide which community should I go to, and then if I, in a community, how much do I consume, how much do I produce. They're also going back to you, so there's a bound on how much time, the total time you have available, and both to produce and the total maximum rate at which you can consume. So it's just time limited. And then you want to form communities to maximize your utility. Basically, you want to allocate time to communities that maximizes your utility over all communities. So it's a sum over all communities. You want to produce content to maximize your utility over all things. And if you do that under this one-dimensional model, the outcome is it's optimal for a consumer to choose one community and read only content in that community. And for producers, it's optimal to produce in exactly one community, and this community focus on one type of content, that is an optimal content, okay? And then, I mean, this would be the research question, is it unique, and so on. Okay, and these are the detailed results, so we have, maybe I don't, so basically the outcome here is we have these interval communities. So, maybe I show it here. A Nash equilibrium would be, if this is the ring of content, there would be intervals of equal size, each corresponding to a community. So all people with that, all agents with this interest that either produce or consume or have their main interest in that interval, they would be in this community. So this would be no non-overlapping community structures of intervals. So that's the, and that's the.
There is no marginalization in that case.
It could. So what can happen here, and that's what's going to happen in marginalization, all the producers are in at least one community, and some consumers, these ones here, would not be in any community. Yeah, it's not that. So here a community consists of, or there are producers. So here we assume there are content producers and content consumers. Under the marginalization, all the consumers are going to be in a community. But all the producers are going to be in a community. But some consumers are not going to be in a community because they will get a negative utility in any of the communities. And you're better off then, because if you don't participate, your cost is zero. And if you participate, your cost would be negative. Does that make sense? Now anyway, okay, I can come back to that later. And then each agent belongs to a single community that produce exactly one type of content that is different from their main interest. Okay, you have a question?
Yes, the community structure is an input to the model, right?
Say again?
The community structure
No,
is...
no. So this is, anyway, so I submitted this paper, and there was one confusion. It's not, it emerges. It's not baked in, it emerges.
So, but the strategy of a player is to produce content of a given type or in a given community?
No. As an agent, I can decide there's a set of communities right now. Which community should I join? How much time should I allocate to consume? How much rate should I allocate to produce? And which content to produce?
So if I can decide to produce in a given community,
yeah.
The community has to exist prior of me deciding to join.
Yeah, but which is the community structure is not given. So basically it's interesting. So you would start out with each person being its own community.
Okay.
And then you would say, look, if I join with this person who has the same interest, my utility would be higher. So you have communities of 2 people. Now you join more. So you actually can look at the dynamics and the community. So you can start with no communities at all, and then people would join communities and the communities.
It's not a static game in a sense.
No, this is a Nash equilibrium. We say this is a possible outcome, okay. But we also show that you actually converge to this type of outcome. You always converge to a Nash equilibrium from let's say there's nothing. After the Big Bang, there's nothing. Then the solar system would emerge. These communities would emerge, but it's not baked in. Okay. So we don't say this is the structure we want. You know, in a Nash equilibrium, we just say if we have this structure, this would be a Nash equilibrium. The question is, dynamically, would this structure emerge? And the answer is yes. Okay. So in a Nash equilibrium, basically you say, look, this is a stable outcome, but you cannot tell whether you actually get to that stable outcome or not. Sometimes you do, sometimes you don't. And here it's nice, it's actually, you always go to a Nash equilibrium. So it's a very well-behaved system. So in a game theory, it's very unusual. You have such a nice system. You always converge to a Nash equilibrium, and the Nash equilibrium is always socially optimal. So social networks, they're very well-behaved, and maybe that makes sense. Does that answer the question a little bit?
Yeah. Okay.
Yeah. No, it starts here. I mean, anyway. So no, these are not baked in. They would emerge. Okay. And also when we look at the kind of the content that is being, it's concentrated among these intervals. So if this would be, maybe I draw it here. So if these are the intervals, so I cut it and stretch it out. So these would be intervals. The content that is being produced would look like this. Okay, basically content would be produced here, content would be produced here, content would be produced here. But there's no overlap between content in different communities, and there's quite a bit of separation. Okay, and this is kind of an outcome of, and this the interpretation would be, I'm not sure, but I can see, for example, at the university departments, they say the courses they offer are often quite different. Okay, even in computer science, they say this is a computer science course, it should be here. So there's quite a distinction between them, and that's what it would say. Okay, and it also says that the closer you are to the center of the community, the higher your utility is going to be. Okay, and this can help us to find communities. So basically, what we can do is we can start at the, let's say, somewhere here, and then we can find people with a higher rank until we get to the middle of the community, and then we can find the whole community. So that's something, I'm not sure whether that makes sense, but that's the idea here. So there are some properties that we actually can use to come up with more efficient algorithms. Okay, so these are the, okay, I'm already over time. So this is a simple model, okay? It's already a bit complicated, but it's the simplest possible model we can think of. We got some results that explain what happens in a Nash equilibrium. The results have something to do with happens in reality. We're now doing algorithms to do things, and these algorithms seem to perform very well. So there is some evidence that these results are indeed useful, okay? But it's still at a very early stage, so more needs to be done, okay? And in particular, where did I talk about it? There are, I mean, certain things we have not looked at, particularly it's the hierarchical structure. So there's simple things that, so then more needs to be done. But I feel now this is promising, okay? Or I go for, I believe interesting things will come out, okay? Maybe at the motivation it seems a bit, that's impossible, what are you talking about? But actually, to be honest, it works surprisingly well. We felt this is such a simple model. It's just an exercise. Probably it won't be very useful to come up with algorithms. And we discovered the opposite. We can use this actually quite well to come up with, even though it has its limitations, it provides some very useful and interesting insights to guide the design of algorithms. Okay, so I'm over time already, so maybe stop here. I'm not sure whether we have time for questions. Yeah, excellent.
How is the metric playing that role?
Say it again.
Metric on the topics.
Look,
So did you, I mean, like if you change the metric, like how does it